as the Metal Injection Molding Association President. He joined Liquidmetal Technologies on March 3rd, 2014, just recently, as the Vice President of Worldwide Sales and Support. Warm welcome for Paul Long.
When we see the hourglass, we know we're in trouble, right?
Go ahead.
Being very stubborn. We apologize for the delay. Oh, here we go. And it's still going. Okay, we'll get started. We'll hope all goes well. Thanks, Mark, for the introduction. I won't spend any more time talking about my background. Although it is kind of interesting to have 30 days ago spent time in my office in Portland, Oregon, creating a presentation for an international conference on metal injection molding, and then just last week spending time in my new office in Rancho Santa Margarita, California, putting together a presentation on liquid metal technology. So I'm 9 days into this thing, and hopefully I'll be able to cover the ground everybody was hoping they might see relative to our technology. So I'd like to talk a little bit about our history today. What is amorphous metal? Some characteristics and properties of the material. What the manufacturing process looks like. Some basic application design criteria. That's what kind of parts lend themselves to the technology. Some candidate applications for liquid metal. We've kind of done a lot of interesting things over the years. Since 2002, formed small sheet material, did thermal forming, blow forming, all sorts of different neat things. Today we're really trying to focus our energy around making small part applications. The metal device market we think is a great market for the technology. And then we'll just kind of compare this process to a few other metalworking technologies to kind of help further define what is the niche for liquid metal. Corporate headquarters are in Rancho Santa Margarita, California. We have a wonderful R&D department there, and it's just some super talent. So 30 years in powder metallurgy, you know, why would I jump ship and go to liquid metal? The talent is really second to none, and as we talk this afternoon or this morning about our capabilities and what we're doing, I think you'll find there's some pretty intriguing potential with the business. So a little bit on the history, this whole idea of amorphous metals or metallic glass, if we're talking about what that material looks like in an atomic structure. First discovered in '62. Some of those early materials required just massive cooling rates. We're talking about tens of millions of degrees Kelvin per second cooling rate to get this amorphous metal structure, atomic structure. Then Caltech came up with a alloy requiring lower cooling rates in 1993. That's really the basis for the liquid metal alloy. It requires less than 10 degrees per second cooling rate that allows us to really get that amorphous technology. The business was public in 2002, and then partnered with Engel and Materion in 2010 and 2011 to produce essentially a full system that you can acquire both materials and equipment to run parts. So 58 U.S. patents are owned, exclusively licensed in addition to foreign counterparts. We, in the last, I think since 2010, have have 55 additional patent applications in around the technology. So those are covering composition, processing, and application of our alloy. We have 2 licensees at this time, Swatch Group and Apple. So some of the characteristics and properties of the material, the initial system was a zirconium, nickel, beryllium, copper, titanium alloy, and with sensitivities around materials like beryllium, the company has recently introduced a beryllium-free alloy. I didn't depict that anywhere in the presentation, but that is available today. The alloy melting temperature is 720 degrees C. We actually heat the material up to that temperature before the injection molding portion of the cycle, the process, and we'll have hopefully if the videos work today, you'll get to see what that looks like in action. So we talked about amorphous alloys or metallic glass type material. If we look at our alloy in the molten state, that top center view, we see a representation of its atomic structure. If you cool that quick enough, essentially you freeze that liquid and you don't change its structure. That's in the bottom left hand illustrated there. Now comparing that to a typical metal where you have crystalline alloy, very different structure and therefore very different set of material properties. The top left-hand view shows us a crystalline atomic structure that's similar to, or representative of most metal materials. We're showing the grain boundaries as kind of the weak regions, the slip planes that are in that material structure, and then the amorphous atomic structure below representing the liquid metal alloys. Lots of data here. I don't intend to walk through all this, but just trying to give some quick comparisons to other materials, particularly in the upper left if we're looking at ultimate tensile strength. By the way, the stainless steel alloy shown there is indicative of physical properties of 17.4 pH before precipitation hardening. So we're looking at ultimate tensile strengths. For those of you that think in terms of KSI, we're talking about 238 KSI ultimate tensile strength. So really great properties on strength. Strength to weight ratio is really impressive. The material on the Vickers scale, 576 hardness, it's about an RC 54 if you were to convert that. And the elasticity of the material is really the unique characteristic, and that's really an artifact of that molecular structure we looked at in a prior slide. Some of you may be familiar with liquid metal golf, liquid metal tennis rackets, some of the early work that was done by this business to kind of leverage that high elasticity of the material. It's for someone like me coming from the metals industry, it's really a unique capability and offers, I think, a lot of promise in a lot of different applications. Surface finish is another benefit of the process. We say better than 2 micro-inch surface finish on almost all cases. So it's really a reflection of the surface finish in the mold. If you have a highly polished tool, you'll end up with a very shiny surface. And we have several parts on display at our table. If you want to stop by, you can get a first-hand look at just how capable the technology is in providing high surface finish. So we're going to see if a video will run here, but it doesn't look like my link is working. Tell you what, come by the booth. We'll show you this video. It's a demonstration of the elastic limit of the material and comparing it to titanium. When I mention the words metallic glass, I often see engineers, product development engineers' eyes roll back in their head and they think, boy, it's a brittle material. How could it be suitable for my demanding application? When you watch this video, it lends a lot of credibility to the alloy and just demonstrates if you're designing within the material strength requirements of your application, it's very, very suitable alloy. So the liquid metal process. Now this will be the one video, if I have to escape out of this PowerPoint just to run the video, I will. But we start with raw material. We looked at that composition earlier. That material is combined into raw ingots. Those raw ingots are then inserted into the molding machine. They're heated under vacuum to protect them from oxidizing. Those materials then are injected into standard injection molds under pressure. We get an as-molded part, and basically once you remove the gate and runner, you're done. That part is finished. This is the molding machine we currently have installed in our facility. We have another one on order from Engel that will be installed this summer. It'll be a fully automated work cell, and you're welcome to come and visit us and see that operating.